Hi, I'm Manis, a PhD candidate at Emory University, and I'm delighted to tell you about our recent work, CrowdTeacher, robust code teaching with noisy answers and sample-specific perturbations for tabular data. A bit of introduction on what crowdsourcing is. Crowdsourcing is labeling unlabeled data by obtaining multiple opinions. There are two main motivations for selecting crowdsourcing to label data that has no ground truth attached to it. First is that expert labeling is expensive, and therefore hiring non-experts can optimize our costs. An example of this approach is detecting community guideline violations on social media websites by asking a bunch of people to mark harmful content. Another reason for opting for crowdsourcing is that in certain applications, getting true labels from a single expert source is not even an option, since the labeling is somewhat inherently subjective, which is why in medicine we sometimes ask to get a second or even a third opinion. Examples of this is doctors detecting stages of a disease from medical images. We look at one practical case in detail, identifying bedsore cases in electronic health records. This is a critical task, since having accurate bedsore rates would help us with a smarter allocation of resources to prevent future cases. Two reasons contribute to uncertainty of labeling for this task. First, bedsore detection involves multiple anatomical assessments, which makes it challenging, and second, even expert nurses might not agree on whether a patient has had bedsore or not. This uncertainty makes formulating this task as a crowdsourcing problem very appealing. Here, the input for bedsore detection would be patients' hospital records and multiple opinions from nurses about their bedsore conditions. In crowdsourcing, there are two different but related problems. Truth inference refers to discovering the real label of tasks from multiple annotations. Two of the most widely used methods here are simply taking the majority class among labelers or using expectation maximization to estimate annotator's reliability and positive class ratio to later use it to weight annotator's opinion and discover the true labels. Learning from crowdsourcing labels, however, refers to learning a classifier that would predict the class without any annotation. Here, the input is multiple labels for our training data, but not their ground truths, along with their features, and the output is classifying test data using only its features without any annotations. Previous solutions for this problem can be categorized into three groups. The first approach is individual annotator modeling, which tries to reproduce each annotator's label for each sample from the so far estimated class probabilities for that sample. The number of parameters for this recreation results in multiple variants of the crowd layer approach, while another approach is called doctorate, which tries to learn a classifier for labels of each annotator and finally learn how to optimally weight these classifiers. The sequential approach is rather straightforward. First, establish some ground truths for training points through an aggregation method and then simply treat it as conventional classification. For instance, we can use EM aggregation method and then apply any desired classifier for our test data. The last approach ties learning aggregated labels problem and the classification problem together through expectation maximization. This approach is rather time-consuming and computationally expensive. We can view the uncertainty caused by potentially conflicting labels in crowdsourcing as noisy data. The approaches we just discussed can directly be applied to combat crowdsourcing noise, but there are also more general frameworks proposed for learning with noisy data. Data augmentation in computer vision and images generates multiple versions of the same data point by applying transformations on the original image. In a quite similar fashion, synthetic data generation also tries to increase the variety and the number of samples used for training by outputting synthetic data points that have almost the same performance as the original data points. A third paradigm considers what samples are used for different phases of training and when it is best to prioritize each sample. CrowdTeaching algorithm is an example of this paradigm that prioritizes more certain samples in earlier training epochs. More details on that later. Some more details on synthetic sample generation. Data synthesizers learn the distribution of features from training data such that using their output, synthetic samples will achieve almost the same performance on test data as using the original samples would have. Synthesizers are helpful in multiple ways. Synthetic data can preserve privacy of sensitive data by replacing original samples for training. Also, in sample sparse settings, it can be used to increase the training size by generating similar versions of the original data points. Once a data synthesizer is trained, we can draw as many samples as we desire from it. Some promising data synthesizers for tabular data are conditional GAN that can handle mixed feature types, both continuous and discrete, in addition to accommodating imbalanced categorical features. For continuous features, CTGAN can estimate non-Gaussian distributions, and for discrete features, it approximates multiple modes. Also, since the generator in CTGAN has no access to real data during the training, it's easier to achieve differential privacy with it. TVAE synthesizers is based on variational autoencoder and can also handle discrete features. And finally, Gaussian copylog, a classical method, is suitable for continuous data, although we can threshold the values to obtain discrete features. Please note that all of these synthesizers are modeled independent of the labels or conflicting annotations. CrowdTeaching is a selective gradient propagation algorithm which of course can be applied to gradient-based classifiers. The premise in CrowdTeaching is that neural networks are known to first learn easy samples and classify more challenging data points in later phases of training. It also assumes that samples lost is a proxy for the sample's uncertainty. So over the epochs, both the number and the uncertainty of samples that are used in backpropagation increases. So here in the figure on the right, you can see that the percentage of low-loss samples increases as the training advances over epochs. CrowdTeaching consists of two identical classifiers with different initializations. Furthermore, to prevent each classifier from overfitting on its own intermediate predictions, each classifier weight is updated with the low-loss samples of the other one. Note the gradient flow propagation shown on the right figure and see how it's alternating every other epoch. Now after that rather lengthy but necessary background, hopefully the main idea behind CrowdTeacher can be understood better. CrowdTeacher tries to connect crowdsourcing noise with noisy learning paradigms. This is achieved through two mechanisms. In the first step, training samples are perturbed through combination with a relevant sample from a data synthesizer. Furthermore, the level of perturbation is proportional to the sample certainty from the crowdsourcing through inference algorithm. In the second step, we feed certainty-aware perturbed data to a modified CrowdTeaching algorithm for learning a robust classifier that leverages the implicit noisiness of the input features from the perturbation step. Here I go through a quick example of how uncertainty-aware perturbations is achieved. Initially starting with our answer matrix here, we have 4 samples and 3 annotators. Source inference is done to estimate class membership probabilities for each sample. Let's suppose given the inferred reliability, the following probabilities are obtained for each sample. We then set the certainty of each one of them as the maximum of these 2 probabilities to get this vector of certainty. Now on the other side, we have our training data of the same 4 samples with 5 features. By feeding this into our data synthesizer, we get some synthetic samples that resemble our feature distribution. Now we do a matching between the original samples and the synthetic ones by choosing one of the similar synthetic samples for each training data. For simplicity here, their index is the same. So first original sample is mapped to first synthetic sample and the same for others. We then obtain the perturbed samples by using a convex combination of the synthetic and training samples weighted by certainty and global parameter perturbation fraction. Here you can see a full view of CrowdTeacher algorithm. Sample certainty is obtained from answer matrix through truth inference method. Perturbed samples are computed by training samples, corresponding synthetic sample, and then sample certainty to be later fed into the code-teaching algorithm to obtain the final model and classifier. For our experiments, we did the following choices for parameters of CrowdTeacher. We used the EM truth inference method given its robustness in previous literature. For synthesizers, we use the three tabular synthesizers I introduced earlier: CityGAN, TVA, and Gaussian coupler. We stick to Gaussian coupler because of its good runtime. For perturbation fraction, we use 11%. And finally, for matching, we did the k-nearest neighbor fitting between the original point and synthetic ones and randomly chose one sample from the top 10% nearest synthetic samples to the original one as its corresponding simulated data. This is how we generate annotations given true label, label density or average number of labels per sample, and noise rate. For this example, we have 4 data points, 3 annotators, and 2 labels for each sample, using -1 to denote annotator, not having a label for that sample. We use beta distribution as consistent with crowdsourcing literature to obtain our reliabilities. Starting from ground truths, we first mark -1 using density and later switch 100 minus reliability percentage of that annotator's one labeling to 0 to get our answer matrix. We did experiments on a synthetic dataset of 40 features and 8,000 samples with 5 feature distributions, each from the 8 continuous and discrete families of distributions. We set the labels for each sample by using a polynomial combination of feature values and thresholding it to get the desired balancedness. Our real dataset for backward detection consists of around 10K samples with 31% of them positive class. Our baselines are using our simple neural network with aggregated labels using crowd layer variants of matrix weight and vector weight with 2 and 4 parameters, code-teaching with no perturbations or V-code-teach, and code-teaching with uniform perturbation or P-code-teach. We repeated all our experiments multiple times across splits and used area under the precision recall curve on the test set as the performance metric. This shows the performance of CrowdTeacher as label density changes. On the x-axis, as the average number of labels per samples increases, we can see that CrowdTeacher keeps its advantage over all the other methods and is considerably achieving a higher average AUPRC. For our real dataset, given the complexity of the tasks, we can still see that CrowdTeacher performs on par with and at some points better than the other code-teaching based methods. We also investigated how the choice of perturbation fraction impacts the performance edge of CrowdTeacher with the next best method, P-code-teach, and observed that although the perturbation fraction can change its performance regardless of its value, CrowdTeacher still remained the top performing method. We also compared what would happen if we used the 2 other synthesizers and observed that even though the trends are different for the different synthesizers, CrowdTeacher still achieves positive gain in many densities compared to the other 2 code-teaching based methods, P-code-teach and V-code-teach, which are shown by circles and crosses respectively in this figure. In conclusion, our method CrowdTeacher combines perturbation of input space with crowdsourcing uncertainty and selective gradient propagation for better performance across different label densities and datasets of varying sizes. Our method is also robust across different synthesizers and the choice of perturbation parameters. Our future work includes incorporating semi-supervised learning into CrowdTeacher and adding new perturbation schemes to introduce more variety for sample perturbation. Thank you for listening to my talk. I'm glad to take questions.